Okay, in this video we're going to talk about the perimeters and areas of similar figures. We've already had a video on what similar figures are. Essentially they're the same shape, just different size. One of them is a blown up version of the other. We also talked about how to solve for pieces, for lengths, for linear lengths of similar figures. So what we're going to talk about in this video is we're going to do it in two parts. We're going to talk about the perimeter of similar figures, and that's a length. Then we'll talk about the area of similar figures. That's not a length anymore, that's area. And so we'll do them separate in the same video, but the first half will focus on perimeter. So we're going to use this first bullet now to guide us. This first rule it tells us is, if two figures are similar. Hey, didn't mean to do all that. Let me fix that real fast. Sorry about that. Okay, so if two figures are similar with a scale factor of A over B, meaning their ratio of their sides is A over B, and it'll be numbers, but we're just making it generic sounding. If they have a scale factor of A over B, then the perimeters of the two figures will have a ratio of A over B. When they say ratio of A over B and the scale factor of A over B, they're talking about the same thing. Remember, scale factor is a ratio, because a ratio, we can usually use it as a fraction, and scale factor is a fraction just with no units of measure, and it's been simplified. So they're saying the same thing. They're saying if the ratio of the sides is A to B, the ratio of the perimeters will also be A to B. But that kind of makes sense. The perimeter of a figure is all the way around, the length all the way around. Well look, that's a side, 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 side. It's made of the sides. So if the sides relate in a certain way, yes, the perimeters will relate in exactly the same way. So ignore the second bullet for now, we'll come back to it. So in this example it says, for the pair of similar figures, find the perimeter of the second figure. If you think you know how to do this, press pause. See if you can set it up. The hint I'll give you is make a proportion starting with what you know. That's half your proportion, those corresponding sides. So hit pause, see if you can set this up. Okay, so what I'll do is I'll go ahead and color code this. Just like we did similar figures, these two sides correspond to each other. Because those two sides correspond to each other, they go on top of each other. I'll do little over big in this example, it really doesn't matter. So I'm gonna do little rectangle over big rectangle. So I'll even label it to remind you, even though it's obvious their size, but just in case. So the little one is 5, and the big one is 8. That right there is half of your proportion. That's also, hint, hint, your scale. That's your ratio of the sides being compared to each other. It doesn't simplify, and if it does, you're welcome to. And if it does simplify, you can, but you don't have to. So that scale, that corresponding sides on top of each other, that's half your proportion for doing any kind of similar figure question. Now over here, we did little over big. We're now looking for the perimeter of the big. Big capital P means perimeter. They are not naming the side P, they're saying capital P means perimeter. What is the perimeter of the entire thing around? We did little over big. We're looking for the little perimeter, so that goes on top because we said little over big. So I'm just going to call that P. Now we know the perimeter of the big. The perimeter of the big is 24. So since big goes on little, 24 meters goes on the bottom. So this is the proportion that you will use when solving this. I probably should have color coded these a little bit better. So those perimeter numbers, that's where we got it on the left. So the 24 meters, let me go ahead and erase that, rewrite that. So 24, go away eraser, 24 meters, that's where it came from. And we didn't know the perimeter of the other one. So the left side was our side lengths and the right side was our perimeters. Remember, corresponding pieces go on top of each other. So now solve this proportion using the same old property you always use, the cross product property. So out of habit, I'm right-handed, I tend to go in this direction first. 8 times P, well that's 8P. Then on the other side, that direction should be easy. That's 24 times 5. 24 times 5, so 24 times 5. 5 times 20 is 100. 5 times 4 is 20, so that's going to give us 120. So we have 8P equals 120. Solve this by getting that coefficient out of there. Divide both sides by 8. They cancel on the left side, and we're left with P equals, 8 goes into 120. I'm going to go ahead and do some long division real fast to help us figure it out. Or some of you might say, let's do this mentally. We know 8 goes into 80 10 times. So if 8 goes into 80 10 times, and we know 8 goes into 40 5 times, well 80 plus 40, that's 120. So 10 times plus 5 times, that's a total of 15 times. So 15. We're talking meters, so 15 meters. So that means the perimeter, the whole distance around the little rectangle is 15 meters. That's what that tells us. The perimeter is 15 meters. So things to keep track of. What's exactly the same is how we set it up. We put the corresponding sides over each other. If you choose to do little over big on the left side, the right side must also be little over big. Be consistent. Put what you know first. You don't have to, but I suggest it. It helps keep you organized. Then put what you don't know. Perimeter is just like any other side because it's made of sides, and so that's why we can do this method. So now let's try another example. We'll come back to the area, what happens with the area in a little bit, but we're going to focus on perimeter for now. So now in these two examples, we'll call these numbers 2 and numbers 3. So number 2 and number 3. We're going to show how we're going to use a proportion to solve for both of these. Now, they both are similar figures that we're assuming that's given right now, and our job is to find the perimeter of the missing figure. We have corresponding sides. Both of these triangles are facing the same direction, so that makes our life easy. That's the left side of that one, that's the left side of that one. You can do big over little or little over big. I'll do big over little this time just for fun. So that means these correspond, so they go over each other. 24 inches over 12 inches. That's the big triangle's left side and over the little triangle's left side. So that will always be equal to the rest of your proportion. So you're halfway done already. Perimeter of the little, perimeter of the big. We did big over little, and so this perimeter right here is the little. And since we did big over little, that's gonna be the little's on bottom. So that 30 inches is gonna be on the bottom. And we don't know the perimeter of the big, so I'm just gonna call it X, or I guess they're calling it P, but you can call it whatever letter you want in your proportion. So now, same thing as always, use the cross product property to help you solve this. Now, some of you might notice, hey, 24 over 12. I can simplify 24 over 12. 12 goes into both of them. That's 2 over 1. If you remember to simplify these fractions inside your proportion, great. You'll have smaller numbers to use. You don't technically have to, but if you want to not feel intimidated and remember it, I suggest you do. So I'm going to say 12 goes into 24 2 times, 12 goes into 12 1 times. So that's going to simplify to 2 over 1. So our proportion we're working with is 2 over 1 equals x over 30. Just because you simplified one side does not mean you have to simplify the other side over here. So now we're going to use the cross product property on this one. So we're going to do 1 times x, which is just x. Then we're going to do 2 times 30. 2 times 30 is 60. So we have x equals 60, which actually in that case that's our answer. We're done, x equals 60. So simplifying it actually was our friend in this case. We got x over 60. So that tells us an x represented the perimeter of the big triangle. So that means the perimeter of the big triangle, meaning all the way around it, all those sides added together, is 60 inches. Is the perimeter all the way around it. Now, if you had not simplified that, you would have just done 20. You would have done 12 times x. You would have gotten 12x. You would have done 24 times 30. 4 times 30. Take a moment to see what that equals. I'll press pause, work it out that way, just in case. What if you did not simplify? I won't spend too much time talking about it, but I'll at least show it to you. So even if you didn't want to simplify it, it's still going to work out the same way. You get 12x equals 720, divide both sides by 12, and you're still going to get x equals 60. So whether you simplify it this step or not really doesn't matter, so don't stress about that. So this was just a what if you did not simplify. So if you want to remember to always simplify, you save yourself some trouble. All right, so now on number 3, we're going to do the exact same thing. We're going to see what do we know about both first, so we can set up our scale, set up our ratio, the first half of our proportion. We know the top right of this one, and we know the top right of the one on the right. So we know the top right of both. I'm going to do a little over big in this example, because again, it does not matter how you set this up. So I'm going to do a little over big. So 12 over 20. Those are corresponding sides, so they go over each other. 12 feet over 20 feet. You're halfway done with your proportion. You now just have to figure out what goes over here, and it's going to be little over big as well. We don't know the perimeter of the little, so since little's on top, the missing perimeter goes on top. Use any letter you want. Now, we do know the perimeter of the big, so that's going to go on the bottom. So we have x over 100. And now just remind you where those numbers came from. I'll do them in blue, 12 over 20. Now, same thing as always, use the cross product property to solve this. I'm going to recommend you simplify your fraction if you can remember to. That makes your life easier. Not the end of the world if you don't. So I'm just going to simplify 12 over 20. We know those are both even numbers, and so 2 goes in both of them, but 4 also goes into both of them. So 4 goes into 12 3 times, and 4 goes into 25 times. So that turns into 3 over 5. I'm going to do that because I like to make my life easy. You don't have to do this step. You could just go straight from here, and that's fine. It'll still work. So now cross product property. 5 times x is 5x. 3 times 100 is 300. And now you just have to be left with getting x by itself. So let's divide both sides by 5 to get rid of it. Divide by 5, divide by 5. You end up with x equals, well, we know 5 goes into 30. 5 goes into 36 times, so let's add a 0 to that, so 60 times. So that tells you x equals 60. So that means that missing value you were looking for in your proportion is 60. And that missing value was the perimeter of the small pentagon. So the perimeter of the small pentagon is 60 feet. All the way around the pentagon is 60 feet, adding all the sides together. So that was another example of using a proportion to solve for the missing perimeter. It's just like solving for sides, but we get to use the perimeter numbers as the other half. So it was a side over a side corresponding, and then perimeter over a perimeter. So now we're going to talk a little bit about how to find the area of similar figures. Let's say you knew the area of one, but you did not know the area of the other. We're going to talk about that now. All right, so let's put the second bullet of this tip at the top to use. It says if 2 figures are similar with the scale factor of a to b, just like here, meaning the ratio of their sides, simplified. If they have a scale factor of a to b, then the area of the 2 figures will have a ratio, meaning kind of like a scale factor, of a over b, except to the second power, squared. Meaning, for example, when we did this problem, we saw that our scale was 5 meters over 8 meters. Well, if you remember how we calculated scale factor, that means that scale factor, because those are already the same unit of measure, the scale factor, the regular old plain scale factor, is 5 over 8. So 5 over 8 is the regular old non-exciting scale factor of all the links, the lines, meaning the sides, the perimeters, the heights. So what that means is if we square that, if we raise that to the second power, so if we do 5 over 8 to the second power, that's going to give us the scale factor, I call it the scale factor or the ratio, same thing, of the areas. So that means 5 over 8 squared. That means 5 over 8 times 5 over 8. So 5 times 5 is 25. 8 times 8 is 64. So that means our area scale factor, the scale factor we will use for all of our area proportions is this one for these 2 shapes. Our area scale factor you get when you square the regular old scale factor, meaning raise it to the second power, which means this. So in this example, our area scale factor was 25 over 64. So just remember, if you can find the scale factor of the sides, okay, or even just the scale, no, actually you need scale factor. So the scale factor of the sides, meaning converting that to scale factor would be make sure they have the same unit of measure. Once they do, you can drop it, so 5 over 8. Simplify it if necessary. 5 over 8 does not simplify, so the scale in this example was also our scale factor. Raise it to the second power, now you've got the area scale factor. This is the one that you will use anytime you want to find the areas of another shape. So now, we're going to do a couple of examples where we're going to find the area of similar figures, but just remember how to find the area scale factor. That's what I want you to focus on, because the only new skill here that we have is how to find the area scale factor, because if you can find the area scale factor, that's then what you're going to use for your proportions. And they're going to look just like this, but instead of 5 over 8, you're going to have 25 over 64, and you can solve for the areas. So to make a quick point, I'll do the example with these rectangles. We'll do an example of saying, what if we were looking for area? So what if that question had said find area? What if it said to find area of the other piece? So let's say we knew the area of this one, and we can actually, at this point, we could find it. For example, if we know that that length is 8, this is a rectangle, so if that length is 8, this length is 8, we know the perimeter is 24, well, those two add up to 16, So that means these two, 16 plus what is 24? 16 plus 8 is 24. These two are equal in a rectangle, so if they add up to 8, that means each of them is 4. So that's 4, that's 4. So the area of this rectangle is length times width, or base times height. 8 times 4, well, that gives you 32. So the area of that rectangle is 32 square meters. And remember, whenever we're talking area, the proper notation is the unit of measure to the second power. We're not saying 32 times 32. We're not saying meters times meters. We're just saying there's a bunch of squares that are 1 meter by 1 meter. There are a bunch of squares, and we have 32 of them inside of this rectangle. That's what that tells us. That just tells us we have 1 meter squares, so meter this way, 1 meter this way. Okay, there's 32 of those squares inside. That's just the notation. So let's pretend that the area was given for this rectangle. Let's say we were already told that it was 32 square meters, and our job was find the area of the little rectangle. So start from scratch for a moment. Okay, this question asked us, here's the area of the big rectangle, here are the sides of two sides of those two shapes. What is the area of the little rectangle? That's what it's asking. Now, because I wrote my area scale factor, that's what you would have done. You still would have found your area scale factor. I did little over big, so we'll stick with little over big. So if you were looking to find area, this area scale factor, that's going to be half of your proportion already. 65 over 64, boom, half your proportion. Now, we chose little over big. Now, so let's see, do we know the area of the little or the area of the big? We are given the area of the big, we're looking for the area of the little. So since big's on the bottom, we're going to put it down there. So that 32 goes down there. So the 32 that let's say we were given the area of 32 of the big one, it goes down bottom over here. Now, we don't know the area of the little. Now, if you just walked up and saw this, not knowing what was going on, you would just be like, oh, that's a proportion. I could solve that using the cross product property. But more specifically, this proportion models the relationship of the areas of these two figures. So we're going to do the same thing we always do. We're going to use the cross product property to solve it. 64 times x in one direction. Remember, you choose what direction you're going first, does not matter. 25 times 32. Those will always be equal to each other. Now, 64 times x, that one's easy, 64x. Now, for the sake of time, I'm going to use a calculator for some of the others, just to make sure we don't get hung up on the calculations. Let's pay attention to the process. 25 times 32, well, that's going to give us 800. So that means on the right side, we have 800. Just like every other equation, get rid of that coefficient by dividing. Divide by 64, divide by 64, those cancel, and now we're left with x equals 64 goes into 800. Let's see, 800 divided by 64 equals 12.5. Tells us the area, because that missing value is the area of the little, 12.5. So since we're talking area, we're going to say 12.5 meters squared. And that's going to be the area of the little rectangle, 12.5 meters squared. Now, if you don't believe me, we're going to prove it real fast, and then we're going to do some examples. We know if the perimeter of this one was 15, of the little rectangle, the perimeter was 15, and we know that this length was 5. That means this length is 5. We know the perimeter is 15. These two add up to 10, which means these two widths add up to the other 5. They're equal to each other, so that means each one is 2.5. So that tells us this width is 2.5, this width is 2.5. So to find the area of this rectangle, we would do length times width, or base times height. 5 times 2.5. Well, 2.5 times 5, let's see what that gives us. 25, 12, one decimal place, so one decimal place, 12.5. So that tells us the area of this one using the old-fashioned length times width method was 12.5 square meters. That's the same way we just got here. So they agree with each other. And let's go one step further. Let's say you still don't believe me. Let's say how do we know that? How do they discover that? One last thing to kind of show you. Let's say we knew the area of the two. Okay, so 32 is the area of the big. The area of the little is 12.5. That's our scale. That's the scale of your areas. That's the area of the big over the area of the little. What you've got to do is you've got to decide, okay, I'm going to turn that into a scale factor. The rules for scale factor was no units of measure and simplify your fractions, so no decimals. What do you multiply 0.5 by to get rid of that decimal? Well, 0.5 times 2, that's a whole number. So multiply that by 2. If you do it down there, you have to do it up there. And if you do that, 32 times 2, well, that's 64. 12.5 times 2. 12 times 2 is 24. So 0.5 times 2 is 1, so that's going to give us 25. So 12.5 times 2 is 25. So we have 64 over 25. Hey guys, does that fraction look familiar? 64 over 25? And now in this case, I did big over little, but look at what we got the first time. We had 25 over 64. That was because we did little over big. So it's exactly the same. So if you'd done this in the other order just now when you wanted to prove it, you could have done times 2, and you'll get 25 over 64. So maybe that one looks better because it's in the same order, but it gives you the exact same thing. So what they found was, people in history who experimented found was the area scale factor of how the areas compare to each other was always equal to the regular old scale factor raised to the second power every single time. And so that's why we remember when we do area, you're going to use the exact same scale factor, but you got to raise it to the second power first. So that's what we're going to do to every single question. So we're going to do 2 examples of that. So in this example, we're told a rectangle has a side length of 2 feet and an area of 10 square feet. So just to help you visualize that, I'm going to go ahead and draw my little rectangle. I know I'm an artist. So length of 2 feet. Length is the longest side, so that means that's 2 feet. And it says it has an area of 10 square feet. So I'm just going to label in here 10 square feet. So I'm just giving information. A similar rectangle has a corresponding side length of 6 feet. This one was 2 feet, this one's 6 feet. So that means this is going to be the bigger one. So I'm going to draw an even bigger rectangle to help you see it. It says that corresponding side to what they gave us. This one was 2 feet, the one that corresponds is this one. So this one's going to be 6 feet. Find the area of the larger rectangle. So what is the area of this rectangle? How many feet? How many square feet? We don't know. But we're going to do what we just did. So if you think you've got this, hit pause. Try it for yourself. Okay, so we're going to start by setting up our regular old scale factor. I'm going to do little over big just because it's the order they're in and it doesn't really matter. You can do big over little or little over big. So 2 feet over 6 feet. That's going to be your regular old scale factor. 2 over 6. Regular old scale factor. Nothing fancy. You're welcome to simplify him to 1 over 3. It's up to you. In fact, I'm going to go ahead and do that just because we know in order to turn scale factor of the sides into scale factor of the areas, we're going to have to square. But scale factor technically, this is just a scale. Scale factor should technically be simplified to begin with. So I'm going to simplify that to 1 over 3. So that's our real actual scale factor of the sides. So now we know the scale factor of the sides. In order to find the scale factor of the areas, we're going to have to square that. Raise it to the second power. So that means 1/3 times 1/3, which is going to give us 1 times 1 is 1, 3 times 3 is 9. So it gives us 1 over 9. So that's going to be our special area scale factor that we're going to use for all proportions concerning area. So area scale factor. So let's set it up. Area scale factor. So that's 1 over 9 equals, if you need help getting to this point and now you think you can solve it, press pause and see if you can solve it from here. So you've got 1 over 9 is your area scale factor. We did little over big. So on the other side, we're going to do little over big. So area of the little over area of the big. Well, we know the area of the little. It's 10 square feet. We do not know the area of the big. So that's your proportion. This proportion is going to model how to find the area of the missing larger triangle. Cross product property as always. 9 times 10 is 90. 1 times x is just regular old x. So there's actually nothing to solve for in this case. 90 equals x. That's great. If that had not been a 1, if that had been a 2, or for example, we'd have a 2x here. We would divide both sides by 2. But that's not the case. So, and that's because we remember to simplify it. We save ourselves effort. So 90 equals x. So that tells us the area is 90 square feet of the missing rectangle. That is not a 2. 90 square feet. That is the area of the larger rectangle. So give yourself some feedback. Make sure you can do that. Make sure you understand how we did that. Focus on, we took the regular scale, turned into the regular old scale factor. We need our area scale factor, so we raise it to the second power, and that gives us the area scale factor, and that's the one you're going to use for your proportions concerning area. We did little over big, so we put the area of the little over area of the big on the other side. So let's try another example. Now take a moment to press pause and try this example on your own first. Alright, so this says a triangle has a side length of 4 inches. So I'm going to just make up a triangle. Triangle and side length 4 inches. So I'll just call this 4 inches. Doesn't matter which side, it didn't say which one. And it says this one has an area of 22 square inches. So 22 square inches. A similar triangle has a corresponding side length of 10 inches. So 4 inches, 10 inches, this one's going to be the bigger one. I made it the bottom last time, so I'll make it the bottom this time. And it says find the area of the larger triangle. We don't know how many square inches, that's what we're looking for. So how many square inches is this one? Same thing as last time. We're going to start by finding our regular old scale factor. Just for fun, I'm going to keep doing little over big. So 4 over 10, these correspond. That's your regular old scale. So 4 over 10 is your regular old scale. So to find scale factor, we have to simplify that. 2 goes into both of those, so that's 2 over 5. That is your regular old scale factor of your sides because it's fully simplified. So your regular old scale factor of your sides, of your perimeters, of any length is 2 over 5. Our area scale factor we get when we square that to the second power. So that means 2 over 5 times 2 over 5 is what that means. And that gives us 4 over 25. So our area scale factor that we're going to use in all of our proportions for concerning area is 4 over 25. Area scale factor. Now if you think you can take it from here, if you were having some trouble, hit pause and see if you can take it from here. Now you know your area scale factor, so that's the one you're going to use in setting up your proportions for solving for area. So 4 over 25, so that's little over big. Just as a reminder, we have to be consistent. So we chose little over big. Now that's going to be equal to the area of the little over area of the big. Well, hey, we actually know the area of the little. That was given. The area of the little is 22. We do not know the area of the big. So since big goes on bottom, we don't know it. I'll just call it X. Whatever letter you want. Whatever letter you want to use. So we got a proportion. We've got our area scale factor on the left, and we've got our area of the little over the area of the big. Solve this using the same thing as always, cross product property. So 25 times 22 will always be equal to 4 times x. 4 times x is easy, that's just 4x. Remember, they're equal to each other. Now 25 times 22. For the sake of time, I'm just going to cheat and use a calculator for now, so I don't have to worry about doing long multiplication when you're trying to focus on the process. So 25 times 22 equals 550. So that tells us the left side equals 550. Just like every other time, divide by this coefficient to get rid of it. Cancels. We are left with x equals 4. That's not right. 550 divided by 4. Divided by 4. Okay. So 137.5. So that tells us that was the missing value. That was square inches. That was the area. So that means the area of the missing triangle is 137.5 square inches. That is the area of the missing triangle. 137.5 square inches. So you used your regular, you used your scale, turned it into your regular old scale factor of your sides, then you converted that to your area scale factor, and that's what we got down here. That's how we converted it. So we use our area scale factor to write our proportion with our area scale factor on one side and then our areas on the other side, solve for the one we don't know. So as long as you're consistent when you write your proportions, either big over little on both sides or little over big on both sides, it sets up the same idea and it's going to solve always the same using the cross product property. So I hope these examples have helped. If you have any other questions, make sure you can use odd numbered questions in your textbook and you can practice them and check your answers in the back of the book to give yourself some feedback. Remember to practice, guys.